Good morning, everyone, and welcome. I am delighted to have you here today. My name is Dr. S.K. Singh, and I hold a PhD in this field. Today, we will be exploring the fascinating world of air handling units. This presentation will cover the fundamentals, design considerations, and applications of air handling units in various environments. I look forward to sharing insights and answering your questions as we go along. Let's get started. Today, we're going to focus on air handling units, or AHUs, which are essential components in maintaining indoor air quality and comfort. Specifically, we'll look at heating, ventilation, and air conditioning, often abbreviated as HVAC, and explore the key components that make these systems work effectively. These systems play a crucial role in creating a comfortable environment, whether it's in a commercial building, a hospital, or even a residential setting. As we go through this, keep in mind how these components work together to control temperature, humidity, and air purity, supporting the overall goal of efficient and healthy indoor air management. Let's talk about the purpose of an air handling unit, or AHU. Essentially, an AHU is a critical component in HVAC systems because it helps control the environment inside a building. Its main job is to circulate and condition air, ensuring the space remains comfortable and healthy for occupants. By filtering the air, it removes dust, allergens, and other contaminants, which improves indoor air quality. It also manages temperature and humidity levels, making sure the space stays warm or cool as needed, and moisture levels are balanced. This is especially important in large commercial or industrial buildings, where maintaining a consistent indoor environment can be quite challenging. The AHU connects to ductwork that distributes the conditioned air to different parts of the building. So, in summary, the purpose of an AHU is to provide clean, conditioned air efficiently, supporting the overall goal of creating a safe and comfortable indoor environment. This ties directly into our broader discussion on how HVAC systems improve building performance and occupant well-being. Let's take a moment to become familiar with the components of air handling systems. Understanding each part is essential because it helps us see how the system functions as a whole. Next, we'll look at their specific functions. Knowing what each component does allows us to pinpoint where issues might arise. It's also important to become aware of potential problems associated with these components so we can troubleshoot effectively. In the upcoming slides, we'll delve into each component in detail, so by the end, you'll have a clear picture of how these parts work together to ensure optimal air quality and system performance. Let's take a closer look at the main subunits. These are essentially the building blocks that make up the larger system we're studying. Each subunit has its own specific functions and characteristics, but together they work in harmony to achieve the overall goal. Understanding these key components helps us see how the entire system operates smoothly. As we go through each one, keep in mind how they connect and support the broader theme of integration and efficiency in the system. This foundation is crucial for appreciating the complexity and elegance of the whole structure. Let's take a closer look at the components overview. Here, we're breaking down the key building blocks that make up the entire system. Understanding these components is crucial because they each play a vital role in ensuring the system functions smoothly and efficiently. As we go through each part, think about how they connect and support the overall goal of the project. This overview helps us see the bigger picture and how each piece contributes to the success of the entire solution. Let's take a closer look at the components that make up this system. First, it's important to understand that each component plays a vital role in ensuring the overall functionality and efficiency. These components work together seamlessly, much like pieces of a puzzle, to achieve our desired outcomes. As we go through each one, I want you to think about how they connect and contribute to the bigger picture. Remember, understanding these components helps us see the system as a whole, making it easier to identify areas for improvement or innovation. So, let's dive into the key parts that form the foundation of this entire process. Let's take a closer look at the components that make up this system. First, understanding these key elements is crucial because they form the foundation of how everything functions together. Each component has a specific role, and their interaction is what drives the overall performance. As we go through these, keep in mind how they connect to the bigger picture we've been discussing. Recognizing these pieces helps us see how the entire process is integrated and how improvements in one area can positively impact the whole. So, let's explore each component in detail and see how they contribute to our goal. Let's take a closer look at some common problems with components. When working with complex systems, it's important to recognize that components can sometimes fail or behave unexpectedly. These issues can range from simple wear and tear to more complex malfunctions. One key point is that defective components can cause system failures or reduce overall efficiency. For example, a worn-out capacitor might lead to inconsistent power delivery, while a damaged sensor could give false readings. Another important aspect is that identifying and troubleshooting these problems requires a systematic approach. We need to understand how each component interacts within the system to pinpoint the root cause of issues. This highlights the importance of regular maintenance and quality control. By catching problems early, we can prevent larger failures down the line and keep the entire system running smoothly. Ultimately, understanding these common component problems helps us design more reliable systems and improve troubleshooting strategies. It ties back to our overall goal of achieving efficiency, reliability, and longevity in our projects. Let's take a closer look at the different types of air. When we talk about air, we're actually referring to a mixture of various gases. The most common type is what we breathe every day. It's called atmospheric air. This air contains mainly nitrogen and oxygen, along with small amounts of other gases like argon and carbon dioxide. Understanding these types helps us see how air plays a vital role in supporting life and various environmental processes. Recognizing the differences between these types is essential, especially when considering issues like pollution, climate change, and respiratory health. So, as we move forward, keep in mind that not all air is the same, and each type has its unique significance in our world. Let's take a closer look at the classification of air. When we talk about air, we're really discussing a mixture of gases that can be grouped into different categories based on their properties and behavior. One key way to classify air is into dry air and moist air. Dry air is the air that contains no water vapor, which is useful to understand because water vapor affects things like air density and pressure. Moist air, on the other hand, contains water vapor, and this plays a crucial role in weather patterns and even in aerodynamics. Another important classification is based on temperature, leading us to hot air and cold air. Hot air tends to rise because it's less dense, which is fundamental in understanding phenomena like convection currents. Cold air, being denser, tends to sink. This classification helps us understand weather systems and how air moves in our atmosphere. Finally, we can classify air based on its composition, which is mostly nitrogen and oxygen, but also includes trace gases. Knowing the composition is vital because it influences everything from breathing to how aircraft engines operate. Understanding these classifications helps us grasp the behavior of air in different situations and how it interacts with our environment and technology. This is a foundational concept that ties into the overall theme of how air influences both natural and engineered systems. Today, I want to focus on filter classes and why they're such a vital part of our overall system. Essentially, filter classes help us categorize and manage data more efficiently. They allow us to define specific criteria to include or exclude certain data points, which makes our processing much more targeted. Think of filter classes as a way to streamline our workflow, ensuring that we're only working with the most relevant information. This not only improves performance, but also helps us maintain clarity in our data analysis. Most importantly, understanding how to set up and utilize filter classes effectively ties directly into our goal of creating a more flexible and scalable system. They give us the power to adapt quickly to changing requirements by simply adjusting the filters, rather than overhauling entire processes. So, as we move forward, keep in mind that mastering filter classes is key to optimizing our data management and making our solutions more robust and adaptable. Let's take a closer look at the classification of filters. When we talk about filters, we're really discussing how they are organized based on their characteristics and functions. The first major category is linear versus nonlinear filters. Linear filters are those that operate based on linear systems, meaning their output is directly proportional to their input. These are common in many applications because they are easier to analyze and implement. Nonlinear filters, on the other hand, involve more complex operations and are used when linear methods can't effectively handle certain signals, especially when noise or distortions are nonlinear in nature. Next, we have the distinction between finite impulse response, or FIR filters, and infinite impulse response, or IIR filters. FIR filters have a finite duration response to an impulse, which means they settle to zero in a finite amount of time. They are appreciated for their stability and linear phase characteristics. IIR filters, however, have an infinite duration response, which makes them more efficient in terms of computation, but requires careful design to ensure stability. Another important classification relates to their frequency response characteristics. Some filters are designed as low-pass, which means they allow signals below a certain cutoff frequency to pass through while attenuating higher frequencies. Conversely, high-pass filters do the opposite. They block low frequencies and let high frequencies through. Then there are bandpass filters, which only allow a specific range of frequencies, and bandstop filters, which block a particular band of frequencies. All of these classifications help us choose the right filter for a specific application, whether we're dealing with audio processing, communications, or other signal processing tasks. Understanding these categories ensures we're applying the most effective filtering techniques in our projects. Now, let's take a closer look at the pressure cascade solids protection from cross-contamination. This concept is crucial in maintaining the integrity of pharmaceutical processes. Essentially, it involves a carefully designed pressure cascade system that helps prevent solids from moving from one process area to another. By establishing a pressure differential, we can control the flow of materials and minimize the risk of cross-contamination. This is especially important when dealing with sensitive products or multiple batches. Highlighting this point ties back to our overall theme of ensuring product quality and safety through effective containment strategies. Remember, implementing a pressure cascade not only protects the product, but also enhances operational safety and compliance. Now, let's take a closer look at the concept of pressure cascade sterile protection. What this means is that by creating a controlled pressure difference, we can effectively prevent microorganisms and particles from entering a sterile environment. Essentially, the pressure cascade works by maintaining a higher pressure inside the clean zone compared to the surrounding areas. This ensures that any potential contaminants are pushed outward, rather than inward. It's a fundamental principle in maintaining the integrity of sterile spaces, especially in sensitive industries like pharmaceuticals and healthcare. So, the key takeaway here is that managing pressure levels carefully creates a barrier. It's like a protective wall that keeps microorganisms and particles at bay. This approach is integral to the overall theme of contamination control and ensuring product safety and quality. For further support, please contact us. We're here to help with any questions or additional guidance you might need after this presentation. Thank you so much for your time and attention today. Remember, we're committed to your success, so don't hesitate to reach out if you need anything.